do with this, create a week 65 namespace. Quad this is hash week 65. Quad this is week 65 of Perl Weekly Challenge. I'm going to have another go solving the problem, editing the footage. So before I get on with the solving the problem, another shout out to Mohammed from the Perl Weekly Challenge team. He hit the nail on the head here with how typing and thinking blend together. Right, so you sort of learn to think with the language that you use. And this is probably true of any programming language that you learn to use. Helps to inform your approach, although in many cases your macro view, your sort of overall approach, you know, if you were to write out the pseudocode of your solution, might be the same across different languages, and then some of the biggest differences might be how you approach the subtasks as you break down each part of your solution. Also happy to see that Mohammed has been producing videos himself of Perl and Raku solutions, and was quite relieved to see that his approach to the matrix problem, the minimum sum path last week, is basically the same approach as I had, where you find all of the possible paths and then find the sums of all those paths and just return the one with the minimum sum. Anyway, it was nice to see how our approaches were kind of similar on the macro level, even if the details are a bit different. Anyway, yeah. Just want to say that was cool. Let's get going. Let's go. Task 1, digit sum. You're given two positive numbers, so they look like scalars here, n and s. Write a script to list all positive numbers having exactly n digits where the sum of all digits equals s. This is quite a nice one in APL. I think I've seen this type of problem before. So we can find out what all of the 3-digit numbers are. So 3 takes 0 gives us a 3-element vector. If we look at something like quad D, this is all of the digits as a character vector. This is all the characters 0 through 9. And if we do an outer product catenation selfie, we can combine them all themselves. And if we do this to the power 2, then we get 4 digits. So this is equivalent to the digits catenated with the digits. And if you do that again, then you get the third one. Quad D catenated outer product power -1 plus alpha. Oh, use right tack to separate the argument. No? Oh, this guy. Yeah, exactly. So here's all the combinations. It's quite large. Of 3-digit numbers, including leading zeros, which probably we don't want, because they'll just actually be 2-digit numbers. So we can drop one from the result. And if we use the rows user command, -fold equals 3, then our long output is truncated. So this is one way of generating all those numbers. So if we do it for 2, then we get 2-digit numbers. Do it for 4, we get 4-digit numbers. Right, so at this point, it's at least a couple of lines, this function. So our character versions of the numbers, which I'll call the digits D, maybe. No, okay, let's say that n. N is this thing, it's 1 drop quad D outer product catenate iterate -1 plus alpha times quad D. Then our digit, to convert a character string, character array of numbers into a list of numbers which can be summed together, we can do execute each, which will convert each of these numbers into an individual scalar number, and then if we add those up, we can sum up the digits. So that's all we're going to do. And it's +/each, execute each. So we get as far as here's n. 1 take n is this. So 1 take n is this matrix. If we execute each of those, sum each. It's a little nasty, but it gets us the sums. And then equal to s, so that's omega for us. Here's the matrix where 1s indicate the sum is equal to omega, which we set as 4, I think. So 4, 4, 4, 4 up here. So we get 1s corresponding here. Actually, raveling the whole thing first, or even mixing, I'm not sure. Raveling the whole thing first is going to help. So yeah, it's a shame this is so loopy, but I'm just, I'm trying to do this quick, not the best possible solution. And then it's where the sum is omega, compress out n. Oh. Yep, I think that's it. So 2 digit sum 4, 13, 22, 31, 40. Boom. Yep, pretty straightforward, that one. Palindrome partition. You're given a string. I'll scale the strings, but it will be a character vector for us. Write a script to print all possible partitions that gives palindrome. And this is all is the maximum length of the partitions 2? Oh no, it's any non-overlapping partitions. So testing for a palindrome is easy. Does the reverse match the original? Race cat, it's not true. Race car, that's true. That's the palindrome idiom. And again, it's looking like we're going to create all the partition things and just filter out the ones which are palindromes. Yep. So numbers up to the length, and these are all the rotations. If we mix this, it might look a little... Oh, it's an identity matrix again, dingus. So the most efficient way to make an identity matrix is the L by L reshape. 1 taken by 1 plus L gets count of omega. 1 comma neg 1 drop, or possibly 1 at 1. This one seems better. Okay. The problem doesn't seem to specify if you could have 3 partitions. If its length is greater than 1, it doesn't seem like single characters are valid from the examples. So 1 is less than the count, 1 is less than the count, and it's a palindrome. There we go. ABA isn't taken account. So it really probably want a stencil. I reckon a stencil is going to do us what we want. So if we do enclose stencil table 2 omega, but we need more combination. Or we just we should really improve our partitioning Boolean vectors. We could go to our old tried and trusted method of generating a buttload of Booleans. Bit reluctant because it's an incredibly wasteful solution. Right, the ABA surely comes from something like this. Yeah, okay, screw it, we're going to do that. Make all the Boolean numbers of length 3, for example. 2 to the power 3 is 8. Indices up to 8. 2 base power negative 1. Oh no, we were right the first time, and in fact it's neg 1 plus. Right, there we go. So that's 0, 0, 0 up to 1, 1, 1. That's all the Booleans of length 3. And then we can get all of the ones of length 7, or of length of omega. At this point, we definitely need to create a function. And it's ABAB. And we start with our partition vectors. Oh no, we start with our length. Right, length is the tally of omega. Partition vectors, all possible ones. Convert into base 2. Negative 1 plus all the numbers from 1 to 2 to the power Oh yeah, I'm gonna make sure we localize quad IO L. Okay, might as well call it len at least, for readability's sake. And probably want to transpose it because we're going to use rank. Then our partitions will be pvec partition rank 1 omega. Why is it saying that, are these long character vectors that are palindromes? Oh, that's so annoying. Okay, for example, if I do the 3 squad parts, I get the 3rd row. And you can see clearly there's no spaces in these. So we can also ask, for example, take the 2nd one. We can ask, is space member, looking at each. Alright, and we don't want that. So NAND space. I don't think I've ever used NAND before, and I'm not sure it's right. It's not this and not that. That's the problem. Whereas we want not that and that. So shamefully, we won't be using. We'll use the top. We'll be inverting there and using and. Never mind. NAND goes unused again. And there's no. The rest of it. Well, these two want to be true, so. And 1 is less than the count, and it's a palindrome. Which, to be fair, like, in this particular case, because it's quite a lot of stuff being put together like this, and I'm using trains, it's unlikely that I'd get much optimization from putting what is probably the cheapest test first. I'll do it anyway just for sort of style reasons, but in some, there is a thought that if there was a really clever interpreter that could read along this and see the tests right, it's a bunch of things ANDed together, so they all have to be true for us to return true, which means we could quit early if this one's not true. But I don't think that will be happening in this case. Maybe it will. Anyway, so, and I also think that I've just done it. That doesn't look. Oh yeah, there we go. That's right. We just wanted the first one. Brilliant. This could be the whole test. We'll probably name this test. Right. All of this. Let's name it in the function. We'll name that as PP test. Palindrome partition test. Is PP? You say this. I was thinking of using PP test to filter out each of the parts instead. This is something more like enclose. I'm still doing this rank 1 to be fair. Enclose PP test omega compressed by PP test omega. That should be it, and then we need to see what the result is if there are none. It could be the empty character vector. I don't think it's that likely. To be honest, well, let's find out. Oh, we got all. Okay. We want unique ones. That helps a lot. If we just get the unique ones, we can see AABAA there. We can see. This is what we really want. AABAAB. This, okay, yeah. This is one of the cases here you can see. Let's say it's AAAA and 14 index parts. Right. Here's an example of one that isn't specified by the problem definition. It says non-overlapping partitions, but it doesn't specify... I mean, all the examples are partitions of length 2. And in this case, they're contiguous, but they haven't got AA like we have here. Shape of that. That's all of them. So it's filtered out none of them. 9 is valid, 19 is valid, but 14 is not valid. So can we devise an argument that will have a flaw in this case? So ABBA BA was getting us pretty close, and then what do you want? If we attach another just the same, like CDDC. This is opening a can of worms a bit because it's obviously going to be much larger, the list. But you can see we have a couple of these contests now. We'd want DDCDC, CDDC, ABBA. No, we wouldn't want ABBA because that's covered by ABBA and CDC. And has ABBA and DCD as well. So we'd only need BBABA. What is that one anyway? ABBA, DD. No, ABBA, DCD. No, wait. Right. Here's PAL index of ABBA, DCD. 41. ABBA, DCD. It's contiguous, yeah, okay. And then this becomes CT. And this is PP, CP, and we'll see. Okay. Nothing errors, but let's look at first of all. Oh, oops. Okay, no single characters, they're palindromes, not just a bunch of spaces. Then, or not containing spaces. And all of our partition vectors, just the ones which will okay, I'm not 100% convinced. That's something. Oh, you after all that? After all, I think I found a minute ago, didn't I? We did this with the 1 is the sum or 2 is in there. And I didn't filter out anything. So I just wasted that 10 minutes. So what was my other approach? Okay, one thing you can do is shape of each. We know how to get rid of blanks. It's not the problem. The problem is we want to get rid of that which is a member of another. In this case, being a member of a different one means... no. Yeah, okay. Because the first one's a member of itself only. So the and/ membership. The only one for which that's true. Yeah, okay. The real unique. And there we go. AA, BAA, AA, BAAB, and ABA. We remove the blanks. We remove ones which are members of others. ABAB. Oh. Here's a palindrome, here's a palindrome partition, and then finally give us the unique ones. Oh, the unique. Right, and we'll get to the -1 case in a moment. Otherwise, just return it. Oh, there we go. So that's our first test case. We finally got it giving the right answer. What was that other one again? AAB, AA. Oh no, ABBA, BA, CDDC, DC. This gives us ABBA, DCD. Yeah, okay, it's not doing the contiguous thing the way I thought I was doing it, but to be honest, if I've got enough for the test cases, ABBA, BB and ABA and BAB, you know, it works for both of the example cases. I'm not going to push it for whatever my definition of the rules is. It's also filtering out all those individual ones, which I think is the main thing. So, digit sum was pretty straightforward. The first thing we do is find all numbers with alpha digits. Then sum of digits, number of digits in result numbers. Return numbers with alpha digits whose digits sum to omega. That's the definition. So just put an arrow. No spaces, palindrome, more than one character. All partition vectors of length len. Yeah, it's not. All the other filters do everything. So I might get rid of that then. All partition candidates. Palindrome partitions. Partition candidates. So we're doing our palindrome partition test on each of our partitions. Make sure there's no spaces, that they are a palindrome, there's more than one character. And that gets us most of the way. No empty partitions. Remove subset partitions. Let's see, of course, remove empty partitions and then remove subset partitions. And those are partitions like the AA, which is a subset of AA, BAAB, right? Remove all of those. No palindrome partitions. Otherwise, return the palindrome partitions. For character vector omega, print all possible partitions that give palindromes. Return -1 if not found. Partitions should not overlap. For example, blah 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 blah. CEC, CEF, DE. Haha. As suspected. So yeah, probably 0 is the shape. It's probably the easiest one. So if there are none, return -1. If there are some, return them. Digit sum and palindrome partition. So yeah, in summary, both of these are like build up the entire space of potential candidates and then filter out invalid ones. Cool. Once again, thank you very much for watching. See you on the next one.